So I'll just wrap up. Anyway, Michael Littman's going to talk to us about machine learning and networks. Okay, so listen, enjoy, ask us questions. All right, so there you go.
All right, thanks, Wade. Oh, well, I don't know if that's a good idea. I may fall asleep. So no, I'm not going to quite talk about that. The game plan, as I see it, is to talk about what reinforcement learning is and how it might be useful and how it might not be useful. And in particular, I'm going to split the talk into two pieces. The first piece is going to be about basically a bunch of case studies, things that people have done using ideas from reinforcement learning that have worked and that haven't worked, or basically things. Yeah, so basically case studies like that, right and wrong ways of thinking of something as a reinforcement learning problem. And then I'll talk a little bit about some of the technology, some of the algorithms that are involved. Just to clarify, I'm not trained as an engineer. I've already gotten a couple questions leading into this talk that are very engineering oriented, and I may not answer those questions properly. I see the world as a computer scientist. It's all about algorithms and analysis and applying them to various kinds of problems, but there's really interesting, important engineering to be done, but I'm going to probably not give it the attention that it deserves in this talk. But I look forward to talking to people offline and making whatever connections we can make that way. All right, so what is reinforcement learning? So reinforcement learning can be viewed as a branch of machine learning. There's also, the words reinforcement learning came out of psychology. So that's not the kind of reinforcement learning I'm talking about. One thing that's sort of interesting is that the computer scientists stole the word reinforcement learning from psychology and distorted it beyond recognition. And now some of the psychologists are starting to steal it back. And they're using the word the way that we use it instead of the way that they used to use it. Because basically what we did is we came up, the community, it wasn't me, just a nice way of looking at a class of problems that is a good fit for thinking about living creatures and the problems that they face. But it's also a really important, interesting way of looking at problems for machines, for autonomous systems that are interacting with environments. So viewed the way that I would view it, reinforcement learning is a branch of the machine learning community that's concerned with sequential behavior. In particular, you could view it as trying to remove human activities from the inner loop of the learning process. So a lot of the field of machine learning is involved with setting up problems for the machine to make statistical correlations and connections about. But a lot of these are implemented in a way where it's important that a person sit in the middle of it and actually say, here's what the right answer is. I'm the smart human. You need to learn how to mimic me. And reinforcement learning is very much not like that. It's very much about getting the people out of that and letting the systems be autonomous and learn from their own experience. And so that's what we try to do. The second bullet, making systems that improve with regard to some performance metric that needs to be specified by interacting with the environment, making decisions, observing the effect of those decisions, and continuing in a loop like that. So one way to think about what reinforcement learning is about, it's about programming a system via task specification. So we, the creators of the system, pick what the task is, and we have to specify it in terms of some kind of performance metric, but we leave a lot of the implementation details to the system itself, because it's going to learn and it's going to tune its behavior to what it actually encounters. We might not know at design time exactly what some of the details are going to be, so we let the learning system take care of some of that on its own. This can happen at a bunch of different levels. So I'll give one concrete example. I should probably have brought a video about that. But this can happen all the way down for very, very tiny decisions at a very, very low level. I'm going to mention a talk that I heard recently from a job candidate in my department where they were making DRAM allocation bandwidth decisions. So this is happening on a CPU chip. It was deciding the tiniest little decision that a CPU has to make in the inner loop of its processing. And that was all being tuned, and decisions were being guided by with using a reinforcement learning setup. But then you could also talk about controlling highway traffic, thinking about how highway traffic could be optimized. So many, many possible scales that you can apply these ideas. One that came up yesterday that I thought was really cute was we have to ground some of our systems out, we use robotics. Not because we're robotics people, but because it's concrete and people like to watch robots do things. So we had a robot that we were trying to program to get to a target. So it had to turn the right amount and it had to go the right distance to get to the target. And the student who was working on it had clocked everything out and made it so it knew exactly how long it had to turn and how forward it had to go, and then ran it on a slightly different surface. And of course, it just would miss. It was entirely different. The carpet versus the hard wood, the turning wasn't happening as quickly. When it was going forward too quickly relative to what he was expecting. The system wasn't using its own feedback to figure out how far do I need to go. Oh, the surface is different now. I should change those parameters. And the learning systems that we run that do that tend to be very accurate, and they tend to learn very quickly. So that's just kind of a brief introduction. I want to give some caveats. The goal here is sometimes there's hype associated with learning. It sounds cool because, hey, people learn, people are smart, people can solve problems, therefore, we make learning systems, they'll be smart like us. And, you know, there's the promise of that, but the reality is quite distant from that. I mean, really, if you want to think about this as a tool for solving problems, it's a tool for solving problems. It's just another tool that can go in the toolkit along with other things. One of the things that makes reinforcement learning different from other ways of setting up problems is the way that the problem is actually formulated. And so I'm going to focus on a couple good and bad examples of formulating different problems. If you set it up this way, it's not really a reinforcement learning problem, and you probably won't be able to solve it. If you set it up this way, maybe you will. So I'll go through a couple concrete examples to kind of give you the flavor of it. I don't know exactly what problems you guys are interested in. I have kind of a passing familiarity with them, but you guys know your problems a lot better than I do. So what I'm hoping to convey is a sense of, all right, what are the issues that you have to flesh out if you're going to try to turn something into a reinforcement learning problem? And I can help with that, but it's going to require some amount of dialogue. So there's a number of topics like that. I'll just go through them as we go. So here's a concrete example with the robot, because robots are cool. It's not moving. Interesting. I think it's trying to move. There it goes. All right, good. So this is a previous generation IBO robot. It is wireless, so it's a WINLAB thing. It has a wireless card sort of shoved into its rump, which is not the best place to put a wireless card, but it works out okay. And it's trying to learn which way to turn to minimize the number of steps or minimize the time to see the pink ball. So it's got a camera on the end of its nose. It can detect colors. When we have a program inside that can detect when the ball is visible, this is a pink that doesn't naturally occur in nature. So it's something that we can actually detect. And initially, it doesn't know how to do this. All it knows is that it can turn left a little bit. All it knows is it can run one motor command or it can run a different motor command. It turns out that those two commands correspond to turning a little bit left and a little bit right. But the robot itself has to try to piece together those motor commands to accomplish its task. So it's trying to map perceptions, what it sees from the camera. In particular, we just represent it as color histograms. So when you face different directions in the lab, it looks slightly different. There's a little more brown in some directions, a little more white in other directions. So it's trying to map those color histograms to, should I do command 1 or command 2, which turn out to be turn left and turn right. So here's how not to formulate this problem. But it's sort of natural way to formulate the problem. It's what people would naturally do first. But it's a garden path. It's not really what you want to do. So we're going to try to teach the robot which way to turn. It would be a lot easier if it knew which way it was facing. So if it was localized, if it knew, oh, well, I'm 45 degrees relative to where the ball is, or relative to the main axis of the room or something like that, if it has absolute coordinates, then it's very, very easy to tell the robot what to do. We can just say, okay, well, take the difference between the angle that the ball is and the angle that you are now, and if it's smaller than this value, turn right, left, and if it's bigger than this value, turn right. So a natural way if you're trying to engineer a solution to this, a natural thing to do is to break the problem up and say, we're going to first figure out how to localize, and then we're going to use the localization to figure out how to behave. So you have to teach the robot to recognize where it's facing. Are you facing the east wall? Are you facing the northwest corner? And so forth. What are the different angles? It's a reasonable thing to do, and people have set up systems like this. Well, basically what you have to do is you put the robot in all these different positions, you gather the data, and then you have a person write down, oh, when it saw this, that was 45 degrees. You make it what's called a training set, machine learning parlance. Here's a bunch of places that the robot was and what it saw, and here's what the angles were as determined by us externally. We measure it. We pair them up, and then it learns to do the mapping. Now when I see this sort of thing, maybe the angle is such and such. Okay. But from a reinforcement learning perspective, we've already shot ourselves in the foot. To do this, you need the labels, you need the training data. Some person's got to sit down with the robot, walk it through all these different positions, and label each one. Now you're at 2 degrees, now you're at 4 degrees, now you're at 8 degrees. It's not autonomously learnable. There's nothing that we can do to just set the system alone and let it learn those angles, because those angles are being determined by us from an external perspective. So we got to have a human being in it. There's got to be tuning. This is not going to be an effective autonomous system. So here's a counterintuitive alternative. Instead of trying to teach the robot where it is, don't try to teach the robot where it is. Don't care where the robot is. It's none of your concern. All right. So instead, what we're going to do is we're going to give the robot 2 things. We're going to give it the ability to recognize when the goal is achieved. And in the case of the robot turning around, we wrote a little piece of code that said, scan through the image. If there's a color value that's between this and this, then that's probably the pink. We'll call that a goal. And maybe there has to be at least 10 pixels like that. But we wrote that code. Okay. That wasn't learned. Then we need to define some measure of cost en route. Okay, so what is it that it has to be able to? Sorry, this is the one thing. These seem like the 2 things. These are not the 2 things. All right. Anyway, but we do need this. We need a measure of the cost en route. In this case, time. So it needs to be able to keep track of time. If it's trying to minimize the time to the goal, it needs to be able to detect the goal, and it needs to be able to measure time. Okay, so those are critical, and we defined that. But now what we're going to do is we're going to give the robot its actions, so it can turn left and right. We wrote those as well, and some notion of its percept, what it actually perceives, which in this case is information from the camera. So these are the 3 main quantities that are important. The actions, which in this case correspond to turning left and turning right. Percept, which is some information about what the current situation is, which we coded as a color histogram. And it has to have an internally detectable notion of reward, which in this case is the time that has elapsed and whether or not it sees the ball. And that seeing the ball is the goal, and once it's there, it's happy. All right. So we formulate the problem in this way, and now the robot can define locations implicitly. It doesn't have to use our coordinate system. It basically defines locations as to how they relate to the goal. When I see this kind of thing, I'm like 4 steps from the goal, and it's to my left. Right? It's all internal to the agent at that point. It's not being externally defined. So it's a less direct learning problem. It's got more that it has to do, because we're not giving it this sort of notion of absolute objective reality that it can use as a touchstone. But there's no human intervention needed during the learning process. So this makes it an ideal setting for reinforcement learning. We'll just let it go and experiment with the world and create the internal representation that it needs to solve the problem.
Is the robot also learning from the images that it sees other than the ball? Like
yes. That's its percept. So it's getting information about, I don't see the ball now, but I see this percent of yellow in the room. I see this percent of red and this percent of blue. It's got some kind of information about what it is, where it's facing. But they're not angles, right? They're not objectively defined directions. They're just percepts, these fuzzy things. But it can start to associate them with things about the world. When I see this kind of color histogram and I turn left, I tend to see this kind of color histogram next. As long as the room is sufficiently consistent and different enough in colors as you move around.
So is the learning here referring to a situation where the entire experiment is repeated again and again?
The
put the robot in a random position and then
yes.
to go back?
Yes, right. So looking at, that's right. In this particular case anyway, what we actually did is we put the robot down. We let it, it's now experimenting, it's turning left and right. It doesn't know what's going to happen because it's just starting out. But eventually it actually gets to see the goal and it notices the ball and it notices that it's reached the goal. At that point it actually stops and the grad student comes over, picks up the robot and resets it to a random angle, puts it down and starts it again. So it does this trial over and over again. That's right. Different problems have slightly different formulations, but that's, I think a lot of them do look like that. I think there's an animation going on in this advance. That's supposed to be the IVO, but in case that wasn't obvious. All right. So, so reinforcement learning agents can be either a big win or a complete non-starter, depending on how you set up the problem, depending on how you formulate it. So, I gave you one example. I'm going to give you a couple other examples that I've been involved with. Some are good ideas and some bad ideas. So second one that Wade alluded to in his introduction was when I first got to Rutgers, one of the first projects, actually the first research project I did when I got here, was working with some folks at WINLAB and a startup, wireless startup, on trying to do network configuration and diagnosis and repair. So this is another case where the obvious way of setting up the problem is a really bad match for reinforcement learning, and you want to do something slightly counterintuitive. So the natural way of thinking about doing network repair is by doing diagnosis. So you've got a network controller that has some perception, has some measurements that it can take about the network, and it's got some actions or interventions, things that it can do to try to fix things or maybe to learn more. And we want to formulate the problem of letting the network repair itself. The particular thing that we set up, we actually had well, I guess I'll get to this on the next slide, I think. But it was a network. It was a computer that was trying to keep itself on the network, and we did various bad things to it to get it off the network, and then it would have to get itself back on. But looking at this as human beings with an external perspective, we'll say, well, if you want to formulate the repair problem, it's really natural and nice to think, well, first identify the problem, diagnose the problem. That's sort of what we would do, right? And if you can do that, if you can diagnose the problem, then it's much easier to repair because you know what you're dealing with. So maybe the learning problem should be first learn a mapping from symptoms, what you can detect about the network, to some kind of diagnosis. What's really going on? What's working? What's not working? And describe it in some way. But again, just like in the robot trying to localize itself, we need some notion, some external notion of what diagnoses are. We have to train it up with some actual labeled examples. We have to tell it, oh, here, when you see that, that was an example of the DNS server going offline, or that your DNS license was revoked, and that's why you lost things. So we put human labels on those different conditions, which is a very natural thing to do, but it uses our notion of an ontology of what network problems are. It doesn't view the world from the agent, the learning agent's perspective. And it makes it really tough, because then we have to actually go through and tell it everything, and then we're stuck in the middle of the problem again. So the counterintuitive thing that we looked at was, well, let's not have it diagnose the problem and then fix the problem. Let's just have it do the whole thing all at once. So we go straight to the repair. So let's see. The setup was that we were trying to recover from a corrupted network interface configuration, and the notion was that we're going to minimize, or the system was going to try to minimize time to repair. We had two classes of actions. These were all implemented as little Java pieces of Java code. Some of those were information gathering actions, asking whether this, the thing is plugged in, ping its own IP address, see what happens, ping localhost, ping the gateway, do a DNS lookup, just a bunch of natural things that a system might do, or a system administrator might do, to find out what's going on with the network. Then we had a small number of repair actions, things that actually change the network state in a fundamental way. These guys were implemented. They were supposed to not change the network state, but just get information. These were supposed to change the network state. So renewing the DHCP lease was one of them. Taking the IP settings that are currently in the network configuration and overwriting them with something that was previously cached and known to work. Basically putting up a dialog box and saying, human being, please fix my IP settings. This is very expensive because people are slow relative to these other actions, but sometimes what else are you going to do? So the repair actions, ultimately the repair action solves the problem. One of these repair actions has to be chosen, but this additional information can help it choose more wisely which one to do. These are generally much slower, it turned out in the code that we had, than these guys. They could gather a little bit of information and choose more wisely and therefore solve the problem more quickly. So to implement this particular example, just like in the robot example, we had to write some code. The code that we wrote was basically checking if you were at the goal. Instead of seeing the pink ball, now the goal means that the network is working again. The computer can actually access the network. There's no foolproof and trivial way to do this. We had a slightly hacky piece of Java code that did a reasonable job of standing in. And it needs to be able to keep time, so it knows how long it's offline and when it comes back online. And of course, that's very easy to do. So keeping these, setting this up wasn't so bad. So we have a set of actions. We have a set of, well, actually, let me move to the next slide. So once again, the formulation here, there's a set of actions, which in this case, there's some query actions and some repair actions. It's got a percept, which are the results of taking the query actions, what it can learn about the network. And there's a notion of reward, the time to connection. And so we wrote a reinforcement learning algorithm that used that interface with the world and actually put it on a computer, and repeatedly, every 2 minutes, we had it break the network. Eitan Fenson, who was working on this, had a great time breaking Windows network connectivity. We weren't sure that that would actually be a useful piece of code, but it was a fun one to write, and it had something like 7 different ways that it could destroy the network connection, and every 2 minutes it would choose one at random and break the network. Yes?
So, if you have this reward defined,
yes.
So what does it do with the reward in this instance?
It's trying to minimize time to connection.
Well, I know that's...
But how does it do that?
Yeah,
Yes, the first half of the talk I'm just going to talk about problems. The second half I'm going to talk about algorithms.
Okay.
So in this particular case, it collects a whole lot of data as it's exploring of, I tried this in this circumstance, I tried this and here. All right, is the current situation that I'm in more like one of these than the others? What would be the most successful action to take? I can say more about that. But at this point, just how can you even map this to a reinforcement learning problem? And we're just letting the reinforcement learner do its thing after that. And it turned out in this particular case, this is the thing that it did. It ended up learning, given the set of failures that it had and the set of actions that it had, as soon as a disconnection happened, it would ping gateway. And if that worked, it would ping its IP address. And if that worked, it would say, OK, everything looks like it's working. I'm going to have to boot this back up to you. If the ping IP didn't work, it would use the cache settings. But if pinging the gateway didn't work, and pinging the IP address didn't work, and trying to DNS lookup didn't work, then what happened was it lost the DHCP lease. It would just redo the lease, and that generally worked. In, I think, one of the 100 cases, that didn't actually fix it, so then it used the cached IP settings, and that worked fine. Here in the there.
It seems like the learning approach implicitly has some cost associated with it, in that the algorithm has to pass through a sufficient number of iterations to know what works and what doesn't work. And that cost sort of compares with the cost of what you would have to do if you had a human training the system. So why is it that the learning approach is considered better? Or is that not the case?
So there's a couple things to say there. One is that this learning could be happening. In some cases, the learning is happening just while it's doing its thing. Right? So in this case, it was, the system would turn on. It would try to solve the problem. Right, somebody would have to do it, but it wasn't a person. The system did it itself. There was no human being in the middle of the loop trying to keep everything all running, and it certainly didn't require any kind of professional expert who knows about fixing networks. The system was its own expert.
So there's a learning curve there. Like the first few times, it messes up badly, I'm guessing.
So there are issues about exploration in particular. So does the system actually have to, well, when it doesn't know anything yet, it's going to make mistakes. Any system is going to make mistakes if it doesn't know anything. Right? You can seed it with a reasonable first guess if you want, but it can adapt, and it can start doing better than however you started off. There's also the issue, though, sometimes it can be in a local optimum. It could be that it's solving the problem, but it doesn't know that there's a much better solution out there, and it won't try it. So it may have to actively try something that seems stupid for the moment, but is important to getting to a smarter solution down the line. Most of the research in my lab is focused on that problem. How do we efficiently explore and explore as little as possible to get good performance? But a lot of these cases, like in this setup, we didn't do any active exploration. We just said, if you're in a situation you've never been in before, you got to try something. But once you've seen something the second time, just assume that the last time you did it, the data was probably okay. And so it didn't do a lot of exploration, and then it ramped up very quickly. It's a fair question, but
you answered one of my questions. My other question is that during a time which this learning is going on to generate this tree, you're assuming the change is fixed. The failure is fixed. It's not an intermittent failure. So the assumption is that you have a hard failure, and then you learn what goes on to do this proper solution. Is that correct?
I thought you were zigging and then you zagged. I thought what you were saying is, because this is sort of what you mentioned in the office before, is that the problem itself may actually be shifting out from under the learner.
Yes, that's one.
Right, so, and that's true. And most of the experiments that I've done don't try to deal with the non-stationarity. The field as a whole has kind of not really get into this. But in the example that I mentioned before about optimizing bandwidth on the DRAM, things are changing all the time depending on what applications are running.
Okay.
And in his experiments, the guy who came and talked about that, I have his name on the slide. His argument was that it was actually adapting so quickly that there was no need for, and it was no need for remembering past setups, no need for recognizing if you've been in a situation that you've been in before. It's just constantly learning, and it was always tracking when it was finding to be reasonable. So I think it's very application dependent. But the ones that are in an inner loop and making tons of decisions get lots of examples actually, and they can actually adapt pretty quickly.
Okay.
As long as they have right feedback. Did your hand go up as well?
No.
I saw another hand.
No.
Okay.
So,
There it is.
one small question here. This is relating to the stationarity of the problem. So I guess if the problem is, if the environment is relatively very stationary,
Yes.
then you could probably, and if it's just this thing, say, if you know, okay, this is this set of steps you need to do, you could probably hardcode this solution.
Exactly.
But now, since, if, say, the environment is changing slowly, then probably this is the,
Right. So there's two answers to. I see two answers to the non-stationarity issue. There could be at design time, when I'm actually building the system, I may have some idea of how it works, but I might not know exactly. There might be this abrupt change when it actually gets fielded. And so a concrete example that we've hit with the robots is sometimes we build the robots out of Legos, and then we deploy them, and we think we understand that left and right are symmetric. But there have been cases where, because of the design, the physical design of the robot, it doesn't turn left as effectively as it turns right. We didn't know that. It's static. It's true in the world. As soon as we deploy it, it's getting good data and stationary data about that. But there was a big shift between when we built it, what we thought we built, and what actually got deployed. So learning is really helpful in bridging that gap. So even if the world is stationary, there may be a disconnect from design time to deploy time. But then the other one is, after deploy time, if things are shifting slowly, or maybe even shifting quickly, the system really is in the best position to be able to exploit that information to do better. And so in that case, yeah, you want algorithms that are going to be adapting along with it. You don't want to every once in a while stop and say, hey, something seems to have gone wrong, would you please redesign me? All right, so here's another setup where I get asked a lot, hey, you're a learning person, spam filtering, that's really important. I hate spam. And it's true that machine learning has done a lot in terms of spam filtering. It's not a good reinforcement learning problem, and I'll say why. But there is another closely related problem that really is a good reinforcement learning problem. So again, just to compare good and bad examples. So machine learning has done a lot for creating commercial grade spam filters. The problem generally is set up as the input, you get a bag of words, like the email represented as a bunch of features. It has this word in it, it has this word in it, it has this number of links to other websites, and so forth. And then the output that the learner has to produce is this spam or not, or how likely is this message to be spam? As the learning setup, there's lots of data. The data is always changing. Spammers specifically try to thwart the learners. So it's considered to be an example of adversarial learning, where it's not just that the learner is dealing with a changing environment, but the environment is changing specifically to take advantage of the learner. It's good in some ways because there is already a human in the loop to some extent. You're reading your mail and you're like, damn, that was spam. So you could be tagging it, and that information could be going back and creating feedback. There is a problem, though. You don't get feedback on the suppressed messages, at least not right away. Like eventually, you might dig through your spam folder and go, that's why she's not talking to me anymore. She thought I ignored her. And then you could give feedback to the system saying that was not good. Please don't do that again. So it's a natural thing to set up as a learning problem. In fact, that's been happening. If you want to, there is a version of it that's amenable to RL called adaptive filtering, where the idea here is each time there's a reward for delivering a non-spam message. Wait, a reward for delivering? Why does it say -10? That's a cost. Okay, so we'll say there's no, that's not a cost. It's a negative cost. It's a reward. Okay. There's a punishment for delivering spam. It seems like the signs are flipped. And it's going to learn from sparse human feedback. Pitfall is if the spam, non-spam distinction is easy, it's encouraged toward the right behavior by opportunity costs. So that's good. If the distinction's hard, very often these systems will end up delivering all or no messages, depending on how common spam is. So basically, if you set up a big punishment for delivering a spam message and a small reward for delivering non-spam, then it will, a system, if it can't figure out how to distinguish spam from non-spam, it'll just say, I will deliver nothing, that will give me the highest possible reward. And vice versa, it can just deliver everything because it doesn't want to risk the possibility of not giving an important message. So it is really important to encourage smart exploration early on so that it has a good opportunity to learn the distinction. Exploration here means the system presents a message to the user, not because it necessarily thinks it's a valid message, but because it needs more data to distinguish spam from non-spam. So you can actually set this up. There's been some very nice work on it. But here's one that I think is even nicer because there's no human intervention at all. It's not really spam filtering, but it's a spam filtering related problem. So I'm told that in the computer science department, at least as of a couple years ago, spam flows, or messages flow in. Some are spam and some are not. They arrive at a server, and before they're actually delivered to human beings and put into their inboxes, the server runs a set of filter programs on them. That message is spam, is tagged as spam, if it fails any filter in the set. So if any of the filters say this is spam, then that gets tagged as spam. If all of them are run on it and none of them say spam, then it's not tagged as spam. So we can set up a notion of cost in terms of the computation time to process a message. And what we'd like to do is, because once any of the filters say it's spam, at that point you don't have to run any of the other filters, right? It's done its job. It said, oh, this is spam. So what we'd like to do is run the cheap and likely to fail filters first. So if you can really quickly determine something's, it's going to be tagged as spam, you do that and it's done. Okay? We're taking whatever the filters say as truth, right? There's no human being, there's no actual feedback about, oh, but that wasn't really spam. No, we're defining spam in this case as any of the filters say it's spam. So it's nice and clean cut. So anything that's not a spam has a fixed cost. It has to go through all the filters. But anything that is spam, as soon as it's tagged as spam, is out. So we'd like to tag the spam quickly. The output is always the same, right? We're not judging the system on whether or not it correctly tags spam. We're going to build a system that will always give the same answer. It will just give it faster or slower. And we like it to give it faster rather than slower. So the idea here is that the actions are, which filters do what are the order in which I run the filters? The percept are, for each filter, you get to find out whether or not it failed. And we get a reward notion, which is the time that elapsed when the filters run, and at the end we get to find out whether it passed all the filters. You can set this problem up as a reinforcement learning problem. We did this. We had some nice results. They wouldn't let us anywhere near their real mail servers to tag any real mail, so we never really got to do this physically, which is a bummer. But I like the setup, so I figured I'd tell you about it. We did a similar project actually before I came to Rutgers. When I was at Duke, where we did something similar, which is that some algorithms, if you're running algorithms on the computer, like sorting or satisfiability testing, there's lots of little decisions that the algorithms are making. So a sorting algorithm, if you're running something like quicksort, that's familiar to everyone, that you can you subdivide the list that you're sorting, subdivide, and at some point it's small enough that the overhead of quicksort is not worth it anymore, and you just want to use some brute force fast sorting method that works really well on a small list. It doesn't scale well to a large list. But there's this cutover that you have to do. And exactly where that cutover should be depends on, well, when you're sorting lists, how sorted do they tend to be? How really, what is the overhead really of quicksort? How quickly do these algorithms actually run? Which you as a designer might have kind of a sense of, but the computer really knows because it's actually running them and it can measure the time. So what we did is we set that up as a reinforcement learning problem, and it would actually learn when to cut over from one sorting algorithm to another. So we set up the algorithm selection problem as a reinforcement learning problem. The thing that I like about this is the algorithms always give the same results. It's not like trying to sort better, right? It's not trying to, oh, this is a better sort than that in terms of the output. The output is going to be a sorted list. The only difference is how long it takes. And that's a really easy thing to measure. You don't have to, there's no quality assessment that has to go on. It's just, give me the time. And so this spam tagging and the sorting are nice examples of that. And I think those tend to be really well set up reinforcement learning problems. If you have a computation you're trying to do, And the answer is going to be the same, but there's different ways of arriving at that answer. Database query optimization also has this flavor, right? Where it's always going to give this, the database is going to give the same answer, but by ordering the queries differently, you can get that same answer faster or slower. Those are nice. That's a nice setup for learning, because at least it's not going to give wrong answers. All right, so network routing is one that people have looked at. So now I'm getting more at networking related stuff that I think would be more applicable in this setup. Network routing, I looked at network routing a number of years ago. Now what, 15, which is scary. And we came up with an algorithm that we called queue routing. And the basic flavor of it was, well, viewing it as a reinforcement learning problem, a packet arrives at a node, the node has a decision to make, which neighbor should it send it to get to so the packet gets to its destination quickly. The percept, in this case, is just, where am I now and what's the destination. The reward is it gets to observe the arrival time. The arrival time can include things like time spent in queues, time spent in transmission, time spent in retransmission if there's noise or whatnot. And so it can collect, let it, we put a little learner in each of the nodes of the network, we let it do its thing, and here's some plots. So what is this saying? So when in this particular plot is plotting average delivery time, so up is bad, and we looked at two different algorithms in two different traffic conditions. So this is very light traffic. So we had our queue routing algorithm that was learning the neighborhood relationships and the delays, and then trying to route along quickest path. And then just a straightforward shortest path algorithm that just said, okay, I know how many hops it is. I've learned the network topology. I'll just route along the shortest path. In this case, and this is sort of like what you said, there's this horrible thing that happens in the beginning. When the system gets turned on, the average delivery time is really long because in this setup, we didn't give it any knowledge to start. Trying to route a packet to that neighbor, it sent it that way. The packet went around for a while and eventually arrived at its neighbor. Horrible thing, the network got very congested because there's all these packets, clueless packets not knowing where to go. But after a couple seconds of simulated time, it settled out, and they both do really well. In the high traffic setup, what happens is that delivery time starts off pretty good. This is now for a shortest path algorithm. Starts off pretty good, but the network packets are arriving in the network faster than it can get rid of them. And so the network eventually saturates, fills up, and delivery time is this kind of steady high value. Not very good. The queue routing algorithm has this, again, this horrible peak where the packets move around cluelessly and they're getting congested because they're getting injected really quickly. But it actually is figuring something out. And after just a couple seconds of simulated time, it's like, oh, no, I should route differently. I shouldn't route along shortest path. I shouldn't route randomly. I should route this way. And now the delivery time crashes down and actually ends up being very, very good. We set up the network specifically so that it would be bad for shortest paths. This was the network that we used. It has this horrible bottleneck here. And what all the learning algorithm basically learned to do is detect that this path, the short path, like you were trying to go from here to here, this short path tends to be very, very congested if there's lots of traffic, and you can route around it. So that's what it did. It just learned, hey, there's this back door, and I'll use it. And it kind of reached an equilibrium state by experimenting with that. So this was done a long time ago. We didn't have any actual networking people around. So if you had any reason to read this paper, I apologize. It's really very naive as far as actual networking issues and so forth. But recently, Brian Russell, who is in the computer science department, graduated, was working with Wade and myself, did something which is really similar to this. The equations are very, very similar, the setup is very, very similar, but the simulator and the protocol were much more like what happens in real networks. And he got very similar kinds of results. He set up a very similar kind of network to create bottlenecks, and it did smart stuff. So that was, I thought, successful. Thank you.
Okay. Yeah, I have this question. First one is just confirmation. Percept is equivalent to the state. I heard someone different in the field call this state of the edge the same.
In the case where the percept is Markovian, it actually conveys everything that's in the state, then those are the same. In some cases, like the network repair example that I gave, the percepts are very, did the ping work? The state information includes things like what's really wrong with the network. And the learner didn't have access to that. So it had to actually learn to associate what it saw with what was really going on. But in most reinforcement learning research, yeah, it would be actions, state, reward.
Yeah.
Yeah.
So
So
also the state is a little more general.
state is more.
And I understand that.
If you really,
there
I mean,
is,
state engineers know what
exactly.
state are, right? It's the state of the system, the real state of the system.
Okay.
And in simulators, you can have the real state of the system and make that the percent. But in real systems in the world, you never know what the real state is. You just have a clue. So this is our measurement of the state. The percent is our measurement of the state.
More realistic expression.
I think so. Yes. That's
Briefly.
Yeah. So I'm trying to be a little careful. That's why I use the word percent. But if there was an RL crowd, I might have used state because that's what people recognize as filling that slot.
Okay, I guess. I have another one. Another one is you used here Giuliani algorithm. Did you have another option in this? I would like to know why you did choose Giuliani for this program. Is it
Rather than what?
rather than
Shortest path. We compared to shortest path.
no. I mean, other different learning algorithm.
Oh. At that time, that's what everybody was talking about. Now there's a lot more options, and in fact, this reinforcement learning in the routing setting became a whole sub-area, it seems. So there's lots of papers where people use lots of other variants of algorithms. So yeah, there's other implementations out there, but at that time, mainly our goal was just to say, hey, you can think about routing as being a reinforcement learning problem, whereas people were mostly thinking about simple like robot navigation tasks, and we wanted to say, no, there's other tasks that are also relevant. Yes.
This setup, does each node have its own local view?
Yeah. So that's what we did. Yeah.
And
It seemed easier to distribute it that way.
so there's no common notion of the entire network state.
Only for us standing back and
For running the
accumulating.
simulation.
The simulator, of course, has the network state, but each individual learner is, it only knows this. It has a table that says, if a packet arrives to me destined for, so the table has what all the destinations are and what are all my neighbors. And then in the cell of that matrix is an estimate of, if I try to reach that destination by first sending to that neighbor, what do I think the total time is going to be?
Okay.
And so it just keeps updating that table. And each node has a separate table like that.
And my other question is, this sort of implicitly assumes that all the algorithms running in all these nodes are somehow cooperating for a common goal. Is that right?
In this, does it assume that? Not exactly. The only assumption is that there's some kind of temporal consistency. When it does send a packet destined for here through that neighbor, that number means something. That the rest of the network is going to take care of it. If there's a node here that's really obstinate or something, it's like, I don't want to route anything.
Yeah.
Then if it routes along that route, the estimate is going to be, it's going to take forever to reach that, and so this guy will stop doing that. So they really are all individually greedy. They're not trying to cooperate. They're all individually just trying to get the packets delivered as quickly as they can. But of course, if everybody didn't want to deliver any packets, they could just drop them in the garbage, they probably would do that. But we're rewarding them. We're basically saying, your job, I hand you a hot potato. The faster the sooner that this gets to its destination, the more reward you get.
You implicitly have some feedback mechanism also then between source and destination.
Right. So when you send the packet, you have to get an estimate. Yeah.
Your reward.
Right. So this is what happens. We route it. So we're node X, and we're trying to route a packet to destination D via neighbor Y. And when that is sent, we get an estimate back from the one we sent it to about what the rest of the cost is going to be. So we add the queuing time plus the transmission time plus the estimate of what the future is going to be as provided to us by our neighbor. And we compare that to what our total estimate was. And we just bring those two things into closer alignment. This is the Q-learning update equation, kind of the simplest reinforcement learning algorithm, because this is one line. But we showed that if you put one of those in each of the nodes, it does something sensible. There's a learning rate here that you can control, and so if the situation is changing rapidly and these values need to be re-estimated quickly, you can set this learning rate to a high value. So whatever, as new information comes in, it washes out the old information. So it can potentially very quickly adapt. The only problem that we saw, at least in this distributed learning setting, and I don't think this happens if you've got just a single learner, but if you have distributed learners and they're all learning fast, you would occasionally get ringing in the network where like half the network had kind of one idea of how things should be and the other half had a different idea. Packets would get backed up and it would try to route around them and then they'd flow and then this one would say, oh, things are good now, but then this other thing would get backed up and the whole network would just kind of oscillate out of control. So if we introduced packets really quickly and had it learn really fast, it tended to flare. So we tried to come up with various ways of damping it out, but at least 15 years ago we didn't have an answer that we were happy with. But I think that's part of it. Part of it is because you have multiple learners that are presenting, and even if everything is stationary in the real world, the learners make the problem non-stationary. We're doing some research now to try to better understand that kind of ringing behavior, not in a network setting, but in very simple games. With just two players, you can get similar kind of dynamics happening that are actually chaotic. Yeah.
I suppose it would be more beneficial to find out not just the delay to a particular destination along a route, but exactly where the delay is happening, where the bottleneck is.
Right, that would require a lot more feedback coming back, though, right? So once it hits, so this guy's routing, and the delay ended up being here, how is that information going to get back? So if there was a separate probe that went back and took care of that,
if the feedback that came back along the same route, it could just keep
that could be right. And so Brian's protocol had some aspects like that.
Yes.
Not that it didn't specifically say this link is bad. Let's get all that information back. But it would say this path is bad for some reason, and everybody on that path would be informed about it. At the time, we did all our feedback just at the handshaking level. This guy sends the packet and immediately gets some feedback back, and so it's all very local. But you're right. I mean, and there's a zillion different ways to go about this. Some of them are much more useful than others. All right, so I'll mention this one pretty quickly. We looked a little bit at deadlock detection. So basically, you've got a Java system running, and occasionally it deadlocks because the code's not written perfectly. You have a deadlock check that you can run to find out if it's actually been deadlocked, which you can run whenever you want. And if it is deadlocked, it can throw things out. If you run that very often, then the system is spending all its time doing deadlock checks. But if you run it not very often, then the system at some point will deadlock, and you won't know about it until you actually go and run the check. So finding the right interval, how often do you want to do this, that balances those two quantities, we set that up as a reinforcement learning problem. And let's see, so we initialized it with a really bad detection interval, and as it was learning, it was moving around, and then it fell into this narrow range of what it was detecting, how often it was doing these checks. And we computed post hoc, and that was in fact the optimal region. This is like within 99% of the best. So it was able to learn that pretty well. It made some harsh assumptions about how often deadlocks tend to occur, what kind of distribution they followed. But it was, sort of a fun thing to do. So we set it up. The actions here are to do a detection, do a repair if the detect finds that there's deadlock. The percept is only if you run a detection you get to find out if the system is stuck. And the reward is the productive time, which you can estimate if you can't measure directly. You don't know if it's actually gone deadlocked. Here's an example of that. The system deadlocks at some point. We don't check until here that it's been deadlocked. This is all unproductive time. And actually, all the deadlock checks are also unproductive time. So we can measure it. We can at least estimate it after the fact. Here's some other relevant applications. I mentioned, here's the name. I don't know how to pronounce it. Littman, I guess. He came and spoke in the computer science department a couple weeks ago. And I was very excited. I didn't know it was going to be a reinforcement learning talk. He's like, oh, DRAM, memory allocation, how are we going to set up the architecture so that this is efficient? And we have a set of benchmarks and reinforcement learning. So I had a good time. But the problem here was adapting the low-level chip decisions to improve the DRAM bandwidth. And he was finding on the standard benchmarks that architecture people use, the DRAM bandwidth usage was improved by 22%. So he's really able to squeeze additional performance out of it. And these are highly dynamic, very quickly changing. The learning algorithm itself has like has to run in computer clock speed, right? You can't like go call a big subroutine and do the kind of stuff that I would do. He had to actually implement that in terms of transistors and modules and so forth. But he was able to do that. And he was able to put it on the chip, and was on the standard benchmarks get big advantages. So that to me was a really nice example of really low-level learning in a very dynamic, very difficult situation, showing benefits. Another problem, we didn't get to look at this too much, but I think Ivan suggested this a couple years ago, was wireless network rate selection. So trying to figure out how do you adjust the transmission rate, not knowing if delays are being caused by congestion or noise. So there's a little experimentation, a little bit of learning you have to do to tune that. There was an element of this in Brian Russell's algorithm. He never directly tested that piece, so I don't have anything to say about that. Other folks have looked at network routing. One of the things that's interesting is, well, as I'll get to in a moment, there's a bunch of different kinds of learning algorithms. They use the policy gradient approach, which I tend not to do, but I'm seeing how it could be really useful in these kinds of embedded systems kind of setups. So I'll say a little bit about that in a moment. This was my advisor. So this work is that seems very reasonable to me. She worked with her student, Yuhan Chang, on mobilized ad hoc routing. So here the idea was that they were going to tune not only the routing decisions like Q routing does, but also the nodes in an ad hoc network. Where should they go if they're trying to maximize the ability to communicate and they have constraints on where they need to be to connect things up? So they kind of looked at both of those problems simultaneously. Their results, I don't know that the results they're great, but at least they went through the exercise of setting up how would you make this a learning problem. It's tough. It's really tough. Another one that I went, now that Google has this thing where you start typing a query and it fills in the rest for you, this is really great for doing literature searches. So I just typed in reinforcement learning 4 and then looked at all the different applications that came out of Google. And one of them that I didn't know about, but I know the folks who did it, was peer selection in peer-to-peer networks. So so I read the paper, it was very cute. So the basic idea, I read, no, the one on the next slide. So the peer selection in Pdp networks. The idea here is that, again, you've got a decision to make. If you're a node in a peer-to-peer network and you're going to do queries, they have a lot of the same information that are replicated in different places, but they might respond at different speeds. And so in this case, they set it up to do a little bit of experimentation, learn about which sources were producing results more quickly, more reliably, and they use that to tune those decisions. Yes?
So in all these cases, you have to come up with algorithms involving this reinforcement learning. So that's a big problem of its own. To design those, what you do and all these things. Those algorithms, how hard or do you...
So because I live in the community that's supposed to be responsible for creating the algorithms, I always work on that part of it. But really, there's a ton of algorithms now that have already been designed. We have implementations of a bunch of them already. I think that the key problem to focus on, which my community doesn't generally do, is defining reward functions. Like, I have an idea of a task that I want to accomplish. How do I set up the right reward function for that problem? Once I do that, we'll let the learning algorithm do the rest. We don't have to design a new learning algorithm. Not one for each problem, but we have a set of them. One of them is going to be a good idea. Like compilers. Right? The compiler researchers are always writing new compilers. But the fact of the matter is, you have a couple compilers lying around, the rest of us just use those. So I think that the learning algorithms are similar to that. Your job is to come up with reward functions.
So it's about the problem formulation and
that's my claim. I want to mention network security in honor of Wade and other people. I get asked this one a lot, and I want to make sure not to get asked this one because my answer is always the same, which is I can't do anything with this. But network security, wouldn't that be great? People have to adapt. The network attacks are always changing. You need something smart figuring out what's going on. Yeah, look at it with the learning stick. But it turns out not to be a good match. So we want to recognize intrusions, prevent intrusion symptoms or intrusions themselves if we can. It's really hard to define the rewards in a sensible way for network security. I've yet to see anything that I think is reasonable. The system needs to see both sides of the trade-offs. It's a little bit like the spam filtering problem. You don't want to have a learner that learns to solve security problems by turning off the network, right? It's like, I don't want there to be any intrusions. Shut down. That would be unacceptable. But it's really hard to set up the reward function so that that's not the optimal answer. You know, of course, the other side is, or just open up the network and then, hey, let's see, if you have a +1, well, you really want something like +1 for legitimate use and -1 for unauthorized use. But what does that mean? What is legitimate and unauthorized use? It's hard for the learner to have access to that information. Sometimes you have to, like human beings, have to work very hard, and in retrospect they can figure it out. But having the learner do it itself, it's very tough. So even defining what the rewards need to be, you need to have solved the problem of intrusion detection. So somehow setting it up as a reinforcement learning problem hasn't saved you anything, because you still have the problem of doing intrusion detection so that you can define the rewards so that you can learn to do intrusion detection.
So as a network security guy,
Yeah.
I'll throw out my few cents in. Don't feel so bad. This is
Okay.
our problem. This is our community's problem. That we repeatedly have big NSF meetings to discuss what do we need to solve. Oh, we need to solve the metrics issue, right? And the metrics pretty much always come down to, if you let an attack through, your cost is infinite, right? So just shut down the network, as you said. There is, interestingly, a completely alternative approach that's been talked about, which is, all right, you know what, we all have viruses and stuff inside of us. Why don't we just learn to live with it? So let yourself get infected.
Well, some viruses are kind of a bummer, actually, in our box.
Well, they are.
Some are bigger bummers than others. But I did find this paper, again, using the Google completion research method. I found this one. This one I read in detail, and I figured I'd report on. It's a security-related problem, but again, it's sort of turning it on its head. So they call it, I thought this was very cute, actually. They call it something very nice, Pdp Vulnerability Assessment. Like, that sounds important. So what they did is they discovered that protecting a network is really hard to formulate as a learning problem. But attacking a network is actually much easier to formulate as a learning problem, because you can get, every time they eat one of your packets, you get a point. So, so they said, okay, this is what we'll do. We'll set up a learning problem where we attack a peer-to-peer network, and we try to come up with better and better strategies for attacking a network. In this case, there's supernodes. You're trying to query them and that bogs them down. Their setup was they used vectors of target nodes to attack. It's not so important. They used a policy gradient approach, which I'll have to explain in a moment. They ran this in a simulator, but it sounded like a pretty reasonable simulator, not the kind that your normal machine learning person would throw together, but something that actually had real stuff behind it. And what they found is that the reinforcement learner learns better attack strategies than do various heuristics. So they had a set of heuristics that could attack the network, and then they had a learner that was even better. So why is this good? I mean, now you understand the title, right? This is good because if you have a network and you want to assess its vulnerability, attack it and see how well you can do that, and the learner will help you do that. It's not entirely insane, but I thought it was kind of a cheap trick. The actions here are the set of nodes to send to, the percept. In this case, there was no percept. They just measured reward, which was the number of queries that were accepted by the network. And tried to keep our queries out. We're just going to try to push them through. So that was all right. So that's kind of the end of my setup of reinforcement learning problems. What are good ones and what are bad ones? I'll say a little bit about algorithms. We're running low on time, but I just wanted to kind of expose you to this stuff and not really present it in depth. All right, so 3 families of algorithms I'm going to tell you about. I won't tell you about the details of each one of them, but the broad categories are actually really helpful to know about. The one category, the kind of most direct category, is policy search. So here the idea is we're going to take, what we're trying to learn is a mapping from percepts to decisions, or states to actions in this case. And so how can we do that? Well, we could just adopt a policy. We can adopt some mapping from states to actions, percepts to decisions, and see how that goes. And if it seems like it's going well, great. If it seems like it's going bad, let's change a little bit and try to hill climb up to better and better strategies. This is a very, very sensible thing to do if the connection between decisions and what's good and bad is very, very difficult to detect. So you might sometimes just have to try things and see how they work out. So that's basically what policy search is about. There's smarter and less smart ways of doing it. The majority of work, if you find at least in the machine learning community, if they talk about reinforcement learning, they're probably talking about a value-based approach. And here the idea is something different. Instead of trying to directly learn the mapping from what you see to what you should do, it tries to learn an estimate of, if I see this and do that, how well will that work out for me in the long run? So it tries to learn what's sometimes referred to as a Q function, which maps state and action to the future rewards. How good is this going to turn out to be in the long run? This is a nice thing to have, I guess, because if you have this, if for any situation that I'm in, I know how good it's going to be for each possible action, I can make a policy out of that by saying, okay, I'm in this situation. What if I did this action? What if I did this one? What if I did this one? Which do I think would work out better in the long run? That's the one I'll do. So there's the notion of a greedy policy, the policy that maximizes our estimate of future rewards. And that gives us a policy. So, and it's something that's maybe a little bit more direct to learn, because you get to try things in the world and you see how they work out in the long run, and you can update your values based on that. So it's a little bit more straightforward to learn this quantity. It's a little less straightforward to use it, but not so straightforward.
Does this explicitly assume a stationary environment?
Well, no, I would say no, because this mapping could be adapting. If the underlying environment is changing,
So
then this mapping could be constantly updated.
What if you had two identical learners trying to play against each other? Let's say like a prisoner's dilemma.
Yeah, so we have, right, so this is exactly what we're doing research on right now, actually. And two prisoner's dilemmas running Q-learning can actually go into chaos, right, in the mathematical sense. And the values go up and down seemingly unpredictably, but yet deterministically. What we're finding is that the chaos, even though you're looking at the whole range of possible behaviors that come popping out of the chaos, they're all better than the defect-effect strategy for prisoner's dilemma. So it's doing something smart-ish, but it's doing something that is not convergent. But maybe that's okay.
So let me frame it in terms of a more specific example. If
More
one
specific prisoner's dilemma.
if one of the players in prisoner's dilemma is a fixed strategy, let's say tit for tat,
Yes.
and the other guy is learning, I believe the other guy learns tit for tat. But if both of them are
Or it can learn to just cooperate, because at that point, it's just the same.
okay, and so you're saying if both of them were learners,
Simultaneously.
they don't get to the optimal point.
Well, if they can certainly start off at mutual defection and just stay there, which is the Nash equilibrium. It's a sensible answer to this problem. But if you put them, there's a whole dynamic systems analysis that we're trying to do here. But there are starting points that you can start it at where it goes to cooperation. There are starting points that you can start it at where it goes to defection, and there are starting points that go into chaos. And I can show you. If you know this stuff, we really need some help. So I would love to talk to you more about it. But just to finish this story, the third class of approaches that people look at, and this is the majority of what happens in my lab, because I think we're generally attacking these robot navigation problems that are fairly high level, is to take what's called a model-based approach. So here, the learning goes into trying to estimate, well, if I'm in this situation or this state and I take this action, what happens? What's my next state, immediate next state, and what's my immediate reward? So it's just very direct information, and you can train these up very directly, because you just wait you try the action, you wait one step, and you get the result. Once you train this up, how do you use it to actually make decisions? Well, now it's a multi-step process. You actually have to solve the Bellman equation. You have to actually plan with the learned model of the environment to derive what the values are in the different states, to derive what the policies are. So just to kind of summarize the two extremes here, we've got, as you move this way, we're learning something that's more directly useful in the domain, but the learning of that quantity is very indirect. Whereas when we go this way, the learning problem is very much more direct, because it's learning instantly based on, it's getting the feedback instantly. Here's what actually happens. But then the use is much less direct, much more indirect, because it has to go through a whole lot of computation to turn that into a decision. So that's kind of the range of approaches. And in fact, the different examples that I gave you of tasks, actually different ones fit into different of these categories. Some of them were policy search based, some of them were model based, where you actually tried to estimate the dynamics and then exploit the dynamics. A lot of the work is value function based, where it's just trying to estimate values and then makes the decisions off of those. So, so all of these really could be valid. I think for systems that really need to be, like if they're really doing low-level packet routing or something like that, it's very hard to justify a model-based approach because there's a whole lot of computation that has to go on. But we use this for our robotic situations because these methods tend to require a lot of data to be able to do something smart. Whereas as our robot is wandering around on the ground, and it can be very easily picking up information about, well, what does this left action do anyway? And then it can start to generalize that to other places. The robot is so slow compared to the speed of computation that it would be crazy for us not to take all the information we can out of the data and use it right away and turn that into decisions. In the time that it takes the robot to take one step, we can solve the whole system of equations. On the other hand, the packet routing, no, it's not the packet, the DRAM routing stuff happen at this level, where you can be much more reflexive. Action comes in, we instantly update our values, we instantly figure out which one has the highest value, and this can be done very, very quickly. For problems that are non-Markovian, where there's all kinds of hidden information, missing information, policy search is sometimes the only thing you can do, because you have no idea what impact your decisions are going to have because they're unobservable. So you just try them and you just wait to see how it all plays out. So all of these have actually played important roles. Let's see. I think when I wrote this talk, I was much more positive about model-based approaches. I still think model-based approaches are great, but yeah, there's lots of other things that people have done. So actually, in some cases, the model-solving problem itself, even in the model-based approach, you acquire a model of the dynamics. How do you turn that into decisions? That sub-problem is sometimes cast as a reinforcement learning problem. Even though there's no learning happening, there's no external data that's coming into it, the techniques that are being used pretend that the simulator is actually generating real data. So that was true of work that Jerry Cesaro did. One of the great successes in reinforcement learning was the world's best backgammon player. For a while, it was both, including humans. It was better than the best humans. Worked using a reinforcement learning setup that was doing value function-based learning to solve it. Another really cool example, which I'll show you in a moment, out of Stanford, is they have a model helicopter, but a big model helicopter, which you can't see because it's dusty, but there it is. It's just now taking off upside down. It went up, it flipped over, and it launched itself up, and now it's going to do a whole series of tricks that are just completely insane. Like, it's tilted forward. I think it's flying. Oh no, here's what it's doing. It's it's a funny pattern where it's changing in directions and whether it's pointing up or down. Stall turns, flipping upside down, dropping, doing loops. This is insane. So, tailspin. This is all controlled by a reinforcement learner, but the way that it was done, whoa, it's upside down and backwards. Now it's flying backwards and in a circle. I don't think I could fly a helicopter straight. It's upside down again. So what they did in this case is they had an expert flyer take the controls and just fly it through a series of motions so that it can learn about the dynamics of the helicopter. So it's measuring all kinds of things about rotor speed and GPS coordinates and so forth, and it gathers all that data. They take it back to the lab at Stanford and build a model, do learning to actually create a dynamics simulator of this helicopter. Then they use policy search-based methods to actually figure out how to fly the helicopter, but they do it in the model. They do it all offline, and then they upload it to the helicopter, and they do the cool stuff.
So it's supervised learning.
It's not supervised learning. So what's interesting about it is there's supervised exploration. Have a human being take it through not those tricks, but just go left, go right, go up, go down. It's probably more complicated than that, but just learn about the edges of the envelope of the control space. Then they build a model offline, and that's sort of the learning. It's going from that data to a system dynamics description. Then they define those tricks in terms of rewards. They say, okay, we're going to penalize you this much if your tail's not in this position at this time. If you're lower than this altitude, we'll give you a cost for that. If you're at this place at this time, we'll give you a bonus. They set up a whole reward structure, and then they search for strategies that in the simulator give high reward with regard to those reward functions. Then they run it on the real outcome. So just to kind of wrap things up, the reinforcement learning formulation, if you really want to do this kind of thing, you have to think hard about where the rewards are coming from. They have to be computable. They have to be available to the learner so that it has some feedback to decide what to do. Time to goal is a really good one if the goal is detectable, for example. Time to goal is not a good one if the goal is not detectable, like computer security setup that says, oh, I want to, minimize my time until there's no intruders, right? Well, that's hard to do because you can't really write that function. But a lot of cases you can. There's a broad set of applications. I tried to give you a flavor for lots of things that are going on, but it's not universal. This is not the case that you can just, it's not a magic wand. I'm sure you know that. But I just wanted to make sure that you know that I know that. In my lab, one of the things that we're focusing on as much as we can is we're committed to learning from real data. So, which sounds maybe like a funny thing to say, but 90% of the work going on in the reinforcement learning community, people create their own little simulators, and they do all the learning in that little fake simulator. There's no grounding in any sense of reality. So when I got to Rutgers, I named the lab the Rutgers Laboratory for Real Life Reinforcement Learning, RLQ. But the real life part is we're going to try to use real data whenever we can. And so, you guys know about the importance of data. The importance of actually embedding this in a real system and making decisions that actually have an impact on a real system. And so, from my perspective, it would be great to work with folks here on setting up problems, doing data collection, solving some interesting tasks. So that was the pitch I wanted to give.